All right, last thing we'll use MO diagrams is to predict whether a molecule is paramagnetic or diamagnetic. If a molecule is paramagnetic, that means that it has at least one unpaired electron. All right, so somewhere it's got only one arrow in it. And what that means in real life is that it's attracted by magnetic fields. And then the opposite of that is diamagnetic, where we have all paired electrons. And that's repelled by a magnetic field. Most things are diamagnetic, so most things are repelled by magnetic fields. Note that you won't actually observe this in everyday life because the repulsion is very, very tiny, so you can't actually feel it or anything like that. Note that if you have only one unpaired electron and you have a bazillion paired electrons, you're still paramagnetic, right? As long as you have one, you're paramagnetic. So let's take a look at O2. If we take a look at the Lewis diagram, we would think that everything is paired and thus diamagnetic, right? All the electrons are either in bonds or in lone pairs in which we have two there each. However, when we do some experiments, we find that O2 is actually paramagnetic. And so this is a case where the Lewis diagrams or the Lewis model fails us, and we have to go to a more advanced model because what we measure in real life doesn't match what kind of our model predicts. And so that's where the MO diagrams come in. These are much more accurate in terms of this kind of stuff. So again, we have O2, 12 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what we can see here is we have two unpaired electrons, and thus we are paramagnetic, right? So molecular orbital theory is able to predict the paramagnetism of O2, whereas the Lewis diagrams are not able to predict that. We could ask the same question for N2. Remember, each nitrogen has 5 valence electrons, so we have 10 total valence electrons. Here's the molecular orbital diagram for N2. Notice it is different than O2. For example, O2 in the pi area, we have 1 orbital in the lower energy and then 2 in the higher energy, and it's flipped here. Here we have the 2 pi are actually lower energy than the sigma. Anyways, we do the same thing, just fill it up with the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so we can see that all of the electrons are paired, and so N2 is predicted to be diamagnetic. If we try to calculate the bond order, we're going to want to take bonding orbitals minus anti-bonding orbitals. So these guys are in a sigma, right? And then so are these 8, or these 6, my bad, 6, for a total of 8 valence electrons in bonding orbitals. These two are an anti-bonding, which you can tell because the little sigma has a star next to it. So minus 2, and then divide by 2, we get 3, and that makes sense. Our N2 molecule does indeed have a triple bond. Here's just another picture of another MO diagram. This one's for ammonia NH3, just to kind of give you an example of what it's like. You can see here we're mixing the orbitals of the nitrogen with the 3 hydrogens, and you get all kinds of different orbitals. And then here are the kind of electron distributions. Notice how the electrons belong to the whole molecule, not to a single bond. We won't really be taking a look at that level of molecular orbital theory. Again, we're just doing a very surface level look. The main point is, though, as you ask more complicated questions, you need more accurate and thus more complex models. For us in Gen Chem, for most of our Gen Chem needs, the Lewis structures or the Lewis model is totally A-okay. But anyways, you still get a nice intro to some more advanced theories of bonding with valence bond theory and molecular orbital theory. Note that VSEPR is not really a theory of bonding, that's a theory of molecular shape.